Okay, welcome students to video class 28, and we are moving on to module 4, and we'll start with the stability analysis using Bode plot. And you will be in need of 2 or 3 sessions, so I'm calling this video class as part 1 of this. Okay. Okay, in the last part of the video, we have studied something called as the frequency response of a system. Okay, I'm just giving you a recap of that. Say, if you consider, there we have considered an LTI stable system, and when you give a sinusoidal input with a frequency omega, right, you will be getting another sine wave but with the same frequency. Okay, say sometimes that may be like this. So that means this particular, when you analyze this output, you can see that there are two aspects which varies while one remains a constant, that is the frequency. So frequency remains the same. If it is omega, then the frequency of this also is omega. But we can see that there can be change in the magnitude as well as the phase. Okay, that is, for example, if you give a 50 hertz signal, you can see that here also when it comes at the output, you will be having a 50 hertz signal, but the magnitude of that sine wave may be varying, phase as well as may be varying. You won't be getting the same magnitude and same phase, and that depends on the characteristics of the LTI system, right? So similarly, if you have a 60 hertz frequency, the output will be 60 hertz but will differ in its magnitude and phase. So that means this magnitude and phase, in one sense, it varies according to omega, right? The phase and magnitude. Okay, now if you try to plot this, if you try to have this, so the combination of this magnitude and phase response is what is called as a frequency response. Now from the frequency response, you will be able to understand various characteristics of the control system. Now our primary concern of our subject itself is the stability. Okay, so that means you can study about the stability of a system from the frequency response, or in other words, if you can obtain the magnitude response and the phase of the response which is being given by a sinusoidal input. Okay, do you remember, if it is a linear time invariant system, the input will be the same, having the same frequency, but they differ in the magnitude and the phase. Okay. Okay, now Bode plot. Now coming to Bode plot, that is our subject, our topic is stability analysis using Bode plot. Now what do you mean by this Bode plot or Bode plot? This is actually the graphical representation or graphical procedure. This is actually a graphical procedure for determining the stability of a system using, this is very important, using what, using sinusoidal open loop transfer function. Okay, sinusoidal open loop transfer function of a closed loop system. Okay, now let me say something about this open loop transfer function of a closed loop system. We have already studied that, right? So say g of s into h of s is actually the open loop transfer function of a closed loop system, as you all know. Now in the previous lectures, or in the videos, that is, I think it's in the module 2, we have written the generalized form of a g of s. Say, for the meantime, I'm just putting this as k1. Now you will understand why I'm not using k later. Anyway, K is actually called as forward path gain, or whatever you can call it as, or the scale factor. Sometimes, okay, that will be nice. It is called as a scale factor, okay, or gain factor. More than that, it's scale factor. It can be called as a scale factor. There is nothing wrong in that. So this is called as a gain factor. Okay, so it is simply a constant k1 into, say this is of the form 1 plus say into s plus t1 into s plus t2 into s plus t3, etc., okay, divided by s raised to n into s plus ta into s plus tb, etc. Okay, now this is your GFS HFS. Now, how to get this sinusoidal open loop transfer function? Now, what is meant by sinusoidal open loop transfer function? Sinusoidal open loop transfer function is nothing but putting S to be equal to j omega, so that your sinusoidal transfer function becomes g of j omega, h of j omega is equal to k1 into, right, j omega plus t1 into j omega plus t2, okay, etc., divided by j omega raised to n, right, and this is j omega plus ta into j omega plus tb, and so on. Okay, now what is this n? N refers to, we have already studied about this, n refers to the type of the system. N refers to the type of the system, and for different type 0, type 1 and type 2, we have derived the error coefficient and static error coefficient and steady state error. All those things we have studied earlier. Okay, so that is the meaning of this n. N always refers to the type of the system. It's not the order of the system. So in a sense, we have studied that the type determines how many poles are there at the origin, right? This always gives you an idea about the poles at the origin. Now, if n is equal to 0, meaning there is no pole at the origin. If n is equal to 1, meaning there is a pole at the origin. N is equal to 2, meaning there are two poles sharing the origin. That's the meaning of that. So now you got this as the sinusoidal open loop transfer function. Now we need to have a slight change in this form. So for that, what I do is, I want to make this make the constant of each term. These two remains the same. Each term equal to 1. So for that, what I need to do is, I can take t1, t2, etc. outside, so that this becomes j omega by t1, right, plus 1 into j omega by t2 plus 1 divided by j omega raised to n, plus you can take ta, tb, etc. outside, so that this becomes j omega by ta plus 1, or 1 plus, whatever you can call, no problem. So this will be 1 plus j omega by tb, and so on, right? So this will be going in this way. Now this t1, t2, ta, tb, all these are constants, so you can combine all these together, okay, all these constants together, and call that as k. Okay, hope you understood why I took this as k1. So this k can be called as the overall scale factor of this system, so that this can be written as 1 plus j omega by t1, right, into 1 plus j omega by t2, etc., divided by j omega raised to n into 1 plus j omega by ta into 1 plus j omega by tb, and so on. Okay, so this form of this sinusoidal open loop transfer function is what is called as the Bode form of the sinusoidal open loop transfer function. Okay, so hope you understood what must be the first procedure to do this Bode plot. Okay, so you will be given with the g of s, h of s. What you need to do it, put s is equal to j omega and obtain this Bode form. Now I will show you with an example how to get the Bode form from a given open loop transfer function. Okay, now suppose you have been given with an open loop transfer function like this. So this is an open loop transfer function of a closed loop system. Now what you need to, if you want to get this in the Bode form, okay, what you need to do is, so you don't have to, so before putting s is equal to j omega, it will be nice if you can eliminate all these, bring all these constants outside. So instead of that constant you must have 1. So then only you will be getting, getting a form of 1 plus j omega, right? Now, so this is actually, say, call this as s square as well. You have an s square and you have a 2 here. Okay, so that this is going to be this is your transfer function. Now 2 into what do you need to take the listen, so this is 2, you are taking 2 as a constant, so this will be 1 plus this 1 plus s by 2, right, divided by s square into 3 into 1 plus s by 3, right, into 0.1 into 1 plus s by 0.1, right? So that this is actually the constant, the initial constant you have. This is k1, right, k1, and this 2 is actually the common, you are taking the common from this factor. Okay, now you have s square plus 3 into, now rearranging this, you will get 2 into 2 4 divided by 0.3 or 40 divided by 3. So you will be getting this as 40 divided by 3 into 1 plus 0.5s, right? S by 2 is 0.5s divided by s square into 1 plus it is 0.3s, 1 by 3 is 0.3 into 1 plus 10s, right? Okay, now this must be the first step that you should do. So from the from g of s, h of s itself, you may take the constant out and obtain the factors of the form 1 plus s. Okay, now once you get, so now this is not, this is just a open loop transfer function, okay, in the Bode form. Now you need to put s is equal to j omega, then only you will be getting the sinusoidal open loop transfer function in Bode form. So this will be 40 by 3 into 1 plus 0.5 j omega divided by j omega the whole square into 1 plus 0.3 j omega into 1 plus 10 j omega. Okay, is it clear? So this is actually your this is what is called as the sinusoidal open loop transfer function. To be precise, it is the Bode form of the sinusoidal open loop transfer function. Okay, right? So I'll give you one more example. Say call this as example 1 and this is example 2. A simple one. GS HS is equal to, say, 3 into s plus 4 divided by s plus 1 into s plus 0.1. Okay, now in this case what you need to do is, the first step is bring all the constants outside so that this will be of the form, so this can be written as 3 into 3 into 4. You are taking 4 outside. So this will be 1 plus s by 4 divided by s plus 1 into, when you take zero point 0.1 outside, you will get this as 1 plus s by zero point 0.1. So after the necessary calculation, you can see that this is 12. 12 divided by 0 0.1, or this is 12 into 10, or it is 120 into 1 plus 0.25 s divided by, you don't need to convert this because it is already 1, so it's already in the Bode form. So this is 1 plus s into, this is 1 by s by 0.1, meaning 1 by 1 plus 10 s. Okay, now what is so this is actually g of s h of s in Bode form, but we want the Bode form of the sinusoidal upper loop transfer function, so that you may put s is equal to j omega, so that you will get this as g of j omega h of j omega is equal to 120 into 1 plus 0.25 j omega, right, divided by 1 plus j omega into 1 plus 10 j omega. So what's the difference between these two transfer functions? This is a type 2 system. This is a type 0 system. What's the meaning of that? This is having two poles residing at the origin. This is having no poles at the origin. Okay, hope you understood how to get the sinusoidal open loop transfer function in Bode form. Okay, I have just told you that the frequency response is actually a combination of this magnitude response and phase response. Now the next question is, using this Bode form of sinusoidal open loop transfer function, you can have the magnitude as well as the phase of what? Phase of this g of j omega h of j omega. Okay, right? That means both this magnitude and phase is going to vary with omega. So in that case, you can have a plot of magnitude versus omega, right? You can have a magnitude versus omega. Similarly, you can have a plot of phase versus omega. So Bode plot is such a graphical approach. Now in Bode plot, you have, the Bode plot consists of two plots. That is, one is the magnitude plot, okay, magnitude plot. The other one is called as a phase plot. Okay, now what is this magnitude plot? The magnitude plot is, I'll explain. Magnitude plot is nothing but, it is the, first of all, the magnitude has to be represented in decibel. Now the decibel representation of magnitude is 20 log magnitude of g of j omega h of j omega. So you want to get this g of j omega h of j omega, that is the open loop Bode form of open loop transfer function. You can, from that you will be able to get the 20 logarithm of that. Okay, and once you obtain that, that is again a function of frequency. So you can have 20 log omega versus omega. Now there is another problem with this omega. Now what is this omega? Omega is actually a frequency, which starts from 0 to infinity. That means in between you have 1 hertz, you can have 10 hertz, you can have 100 hertz, right? You can have 1000 hertz, you can have 10,000 hertz, and so on. So how will you plot this in a single graph? A normal graph is not sufficient to draw this whole range of frequencies. Okay, now if you have a provision something like this, if 1 can be denoted as 0, if 10 can be denoted as 1, if 100 can be denoted as 2, if 1000 can be denoted as 3, 10,000 can be denoted as 4, how will you denote this? By using something called as log omega. Okay, so if you can plot with respect to log omega, that is actually the magnitude plot or the magnitude Bode plot. The Bode plot actually divided into Bode plot, magnitude Bode plot, and phase Bode plot, and combining these together, you will be able to assess the stability of the system. That is our primary objective. So now the question is how to draw this. So in order to draw this, you need the magnitude plot, the magnitude in decibel. I will just tell you. I will within a short time I will be telling you the reason why you need to take it in decibels or in a logarithmic scale, the magnitude. Hope you understood why I took this omega in logarithmic scale. The reason is just to include the whole high range of frequencies in a single graph. Now, if it is a normal graph, how can you put all these high range and low range of frequencies together in a graph? It is not possible. So for that we use logarithm of omega. Okay, now the plot with 20 log g of j omega h of j omega. What is this? What is this called? 20 log g of j omega. This is very important. You need to understand it very clearly. This is actually the magnitude in decibel. Magnitude in decibel. Okay, so I'll just write you here. The magnitude in decibel is given by 20 logarithm of the magnitude of g of j omega h of j omega. Okay, so that is actually the magnitude. Now what about the phase plot? How will you obtain the phase? Now you'll be able to get angle g of j omega h of j omega. This is quite simple, right? You can consider each term independently and you can find the phase of each term, right? Suppose this is applying tan inverse b by a. Here b is 0, so the phase is 0. What about this? This will be tan inverse 0.25 by 0.25 omega by 1. This will be tan inverse omega by 1. This is tan inverse, and what you want to do is, suppose this is phi 1, this is phi 2, this is phi 3, and this is phi 4. If this is the total, the individual phase of each term, what you need to do is, this is simple. This is phi 1 plus phi 2 minus phi 3 minus phi 4. Okay, hope you understood. And what is this phi 1, phi 2, phi 3? That is nothing but individually take tan inverse b by a for the factors a plus jb. Right? Now all the factors are in the form a plus jb. So from that you will be able to get tan inverse, apply tan inverse b by a to get individual phases of each term, and you will be able to get the phase as this, the numerator phase minus the denominator phase. That's how you will find out the total phase. So once you get this is again a frequent, you can have a plot of angle j of j omega versus, again you need to apply the logarithmic frequency. You need the phase as well as magnitude for the whole range of frequencies. That's what we are going to analyze. So in order to incorporate this, we need to get we need to plot this in a logarithm, the frequency in the logarithmic scale. Okay, frequency in logarithmic scale. So in both the cases we want this also versus log of omega. Okay, now so that means it is not possible to, if omega is this, you cannot plot this in a normal graph. So for to plot such log omega, you need a graph. Okay, you need a graph, something like this. You need a graph with one axis as a normal graph and the other axis with the in a logarithmic scale. Okay, hope you understood. So this axis is in logarithmic scale and the vertical axis is in the normal. So you can plot the phase and magnitude, phase as well as magnitude in the on this vertical axis, while the omega will be plotted along with this log omega. Log omega will be plotted in this scale, in the logarithmic scale. So I'll just show you and such a graph where one of the axes is in the logarithmic scale, the other is a normal scale, is what is called as a semi-log graph. Okay, so hope you had all had one of this. So I'll just show you the semi-log graph paper. So look at this. You can see that say when you you may just look at your personal semi-log graph paper, And just to look at this vertical axis. The vertical axis is just as a normal graph, right? The scale is exactly as a normal graph, equidistant from each other. This one, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 divisions, right? You have 10 divisions, you have again a 10 division. So it is equidistant, and the each subdivisions are also equidistant. That means this is a rectangular graph, right? So one of the axes is a rectangular axis because it is equidistant. Now, what about this axis, the horizontal axis? When you look at the horizontal axis, you can't find a, so look at the space. The space between each divisions are different, and as it moves in this direction, you can see that it becomes narrower, narrower, and narrower, and it becomes so narrow, and finally, you can see that. So this is actually one unit, right? One division. And look at the subdivisions. The subdivisions are not uniform in nature, so this is logarithmic in nature. Okay, now I'll just show you how to plot this. Say I'm just plotting this as 0.1, this is 1, this as 10, this as 100, okay, and this as 1000, and so on. Okay, now what I can do is, this is 0.1, 0.1 into 10, that becomes 1, 1 into 10, that is 10, 10 into 10, that becomes 100. So you can call this unit, this division, as 1 decade. Okay, because this is a multiple of 10. Okay, now what about this? Say 0.1, 1, 10, 100. Now you can also start from 0.01. If it would have been 0.01, then it will be 0.1, 10, 100, and so on. Okay, now for simplifying, I'm just starting with 1. So if it is 1, this is 10. If it is 10, this will be 100. If this will be 1000, and so on. Now, if this is 1 and if this is 10, these points are 1 and 10, what must this 2, 3, and represent? This is 1. If it is 1, then this must represent 2, 3, 4, 5, 6, 7, 8, 9. So these are all 1 radians per second. This is 2 radians per second. So log, since it is omega is expressed in radians per second. So this, if this represents 1 radians, this is 2 radians, 3 radians, 4 radians, up to 9, then this must be 10. Then what about this? Now look at this. Now from this 10, the next division is marked as 100. That means this is the next decade, right? So what must this 2 represent? This is not 12. Okay, do remember, this is not 12. This represents 20. This represents 30, because this is in this all the points inside this block is a multiple of 10 of the previous. So this will be 30, this will be 40, this will be 50, this will be 60, and so on. Now what about this? Once this point becomes 100, then all the values that comes over this region will be again in hundreds, right? So this will be 200 hertz, this will be 300 radians per second, 400 radians per second, and so on. Okay, so you will be understanding it when we do the problem. So at least you must understand that you have a graph something like this. This is what is called a semi-log graph paper, and this, on this semi-log, we will be plotting what? We will be plotting this 20 log g of h omega and angle g of j omega and h of j omega. Now the magnitude has to be expressed in decibel. I will tell you the reason within a short while from now. Okay, now let's us see how to express this magnitude in decibel, and find out the phase from a general Bode form of the open loop sinusoidal open loop transfer function. So here is an open loop transfer function for you, that is, it is k into 1 plus j omega t1 into 1 plus j omega t2 by j omega raised to n. Okay, this is a This is a Bode form, right? This is a Bode form. Now, how to represent the magnitude? The magnitude, this is the magnitude in decibel. It is 20 log of 20 log to the base 10 of magnitude of g of j omega. Now, when you take the magnitude, that is, this is 20 log of magnitude of this whole thing. Okay. Now, this is of the form, say, suppose you have a logarithm of a into b by c. You can write this as log a plus log b plus log c. So similarly, you can write like this: 20 log 20 into log k plus log of 1 plus j omega t1 plus log of 1 plus j omega t1 t2 minus log, okay, minus log j omega raised to n minus log 1 plus j omega ta, and so on, right? So this is it. So that means this itself shows what is the need of representing magnitude in decibel. When you express the magnitude in decibel, this product operation gets converted to addition, and it seems to be quite simpler in evaluation. Okay, now another point is to be noted is that we are not going to draw as a normal graph. We are interested only in the variation of this magnitude with respect to omega. So for that, we will be considering each term separately. We just want to know how each term varies with frequency, and the plot will be an approximated plot. If we are not at all interested in the exact the plot of g of j omega for every frequency. We just want to know the variation of each terms with respect to the frequency. So this will be drawn as some straight lines, or this can be called as an approximated asymptotic straight line. This can be considered, and using this Bode plot, you can find out the relative stability, okay, from the upper loop transfer function. So that all you will understand when we start to do some exercises. Okay, so that is the magnitude in decibel. Now, how to find out the angle of g of j omega, h of j omega? Okay, what is the angle of k? You know that. So how will you find out the angle? Say every term, if you can consider this as of the form a plus jb, the phase of each will be b by a. Here b is 0, right? This is a real term, so this will be 0 minus tan inverse 0 is 0 minus tan inverse what? Omega t1, right? Okay, so this is 0 plus. So this is numerator polynomial j omega t1 plus j omega tan inverse omega t2, etc. minus you need to subtract what? Subtract the phase of the denominator. So this will be tan inverse omega raised to, and we are not sure about this. Anyway, let us consider this phase as call this as j omega raised to n. It depends on whether it will be it depends on the value of n. If it is 2, it's going to be a real term. So we do not know. So we'll come to that later, the phase of these terms. Anyway, it is nothing but it is the angle of this term j of omega term minus tan inverse omega ta, and minus and etc. Okay, so you will be able to get this. This also you can plot with respect to logarithm of force. So angle g of j omega versus log of omega. That is, I'll again so you have got this magnitude g of j omega, h of j omega. So using this you can plot, you can have the plot with respect to omega, and this is just an approximated straight line. This will be drawn as an asymptotic straight line. That is, we are interested only in the variation of this. We are not interested in the exact value. You will understand it later. While this phase once you calculate the phase will be plotted versus logarithmic omega, but this is just as we draw in a normal graph, right? Just as we plot in a normal graph and just connecting each points in a freehand. Okay, but this is not a freehand drawing. The magnitude plot is not a freehand drawing, while phase plot is a freehand drawing. Magnitude plot will be approximated as an asymptotic straight line, even though to be precise it is not exactly a straight line, because we are not interested in the exact value. We are interested only in the variation of this terms with respect to frequency. Okay, hope you understood this much. Okay, now looking at this g of j omega h of j omega, that is your open loop transfer function, you can identify four different I'll be using a different four different factors. One is a constant term. Okay, one is a constant term, four different terms. So this can have a four terms in this g of j omega in this open loop transfer. One is a constant term k, another term is 1 plus j omega t1, okay, and the type is similar to 1 plus j omega t2, 1 plus j omega t3, and so on. So this is another form. Another form is 1 by 1 plus j omega ta. Okay, 1 by, okay, this is another term, that is this term. And another type of term is j omega raised to n. So these are the four different terms that you can find in an open loop sinusoidal transfer function, or in the, to be precise, in the Bode form of the transfer function. Okay, now apart from this, you can have another quadratic form is also is possible, of the form s square, of the form, say something like this: 1 plus j to zeta omega by omega n plus j omega by omega n the whole square. Okay, something of this form, and we will be dealing that. Okay, this can be, say, plus or minus p. We'll be dealing with this in separately. So to start with, we will be dealing only with these four terms. Okay, now we are going to, so what is this actually? You want to find out the magnitude as well as the phase. So we will be dealing it individually. And so first of all, we want to know how these terms varies with frequency in magnitude and in phase individually, so that when you start to plot the Bode plot, you need that idea, especially magnitude plot, how this behaves according to frequency. Okay, so these four terms we will be discussing now, and after doing some problems, we will be considering this quadratic form of the term in a separate way and in a separate session. Okay.